It's the super bouncy ball problem. And so out of a 20-meter high building, a super bouncy ball is bounced. And that'd be kind of fun to do, actually. And here's the first bounce right there. That is the first bounce, right? And then it goes 90% of its height, and then here's the second bounce, and then it goes 90%, and the third bounce, etc., right? On down. Now we know that it goes 18 meters on the second bounce because it goes 90% of its previous height, and 90% of 20 is 18. But it goes 18 up and 18 down. So the first term of our sequence, the distance that the ball will travel between the first and the second, at least the vertical distance, between the first and the second bounce will be 36 meters, right? Now between the second and the third, we'll take 18%, we'll take 90% of 18, so 18 times 0.9, right? And we get 16.2, and then we'll double that, times 2, and we get 32.4 meters. All right, so my next term is going to be 32.4 meters, right? And we know that so we know, because we know it's going to be approximately 16.2 meters high here between the second and the third bounce. Okay, and then we can keep going. Now, but let's go ahead. We know our first term now. We know our first term is 36 meters, right? And because we have the first two terms, we can also, we can see if we have a common ratio already, right? So the ratio is going to be 32.4, and we're going to divide that by 36, right? Take the term and divide by the previous term, second term divided by the first. And so we can see that the common ratio here is 0.9. Is 0.9. So that's kind of cool. So now all I have to do is multiply by 0.9. So it's the same difference, actually. Whether you take the up-down distance, whether you double the distance and take 90%, or you just take 90% of the height, it's going to be the same thing, really. All right, so it's going to be 32.4 times 0.9. So the next term is going to be 29.16. Right, okay, it's going to be 29.16, or let's say about 29.2 meters. And I'm going to leave that answer in, and I'm going to just multiply that by 0.9 again, and I get 26. Then it's going to be 26.2 meters. Okay, then I'm going to multiply that by 0.9 again, and I'm going to get 23.6 meters. Okay, and then let's see, I'll multiply that by 0.9 again, 0.9. I get 21.3 meters. Okay, and then I'm going to multiply that by 0.9 again, and I'm going to get 19.1 meter. Okay, etc. I mean, we could just keep going here. Getting carried away. I don't have to go that far, I don't think. But as usual, I get carried away. All right, so now look. The 36 meters is between the first and the second bounce, right? Just to kind of keep that straight. So this is between the first and second bounce, right? This is between the second and third bounce, right? This is between the third and fourth. This is between the fourth and fifth bounce. This one distance here is going to be between the fifth and sixth bounce. This is going to be between the sixth and seventh bounce, and this one's going to be between the seventh and eighth bounce. Right? So in terms of sequences or terms, this is t sub 1 right here, right? This is t sub 2. I'll just even put just a little t there, right? This is going to be t sub 3. T sub 4 is going to be the distance of the bounce between the fourth and fifth term. T sub 5, we can see that, right? T sub 6 right here. And this is T sub 7. All right, so let's see if we're answering any of these questions. How far does the ball travel up and down between the first and the second bounce? Well, it's going to be 36 meters, the first term. Show that the number of meters the ball travels up and down between bounces are terms of a geometric sequence. Well, we just did. The ratio is 0.9. We're good. All right, see, find the number of meters the ball travels up and down between the sixth and the seventh bounce. Well, between the sixth and the seventh bounce, that's going to be Right here, we just did 21.3 meters. That's how high the ball, that's the distance the ball is going to travel on the between the 6th and the 7th bounce. All right, we're good. Now we're on D. Find the total number of meters the ball travels between the 1st bounce and the 7th bounce. All right, well, between the 1st and the 7th bounce, you know, it's going to be the partial sum of the first 6 terms. Do you see that? Because if we go to the 7th term, that's going to add the bounce between the 7th and the 8th, right? We just want the first 7 bounces. All right, so it's going to be S sub 6, because that's what this term is right here, S sub 6. I wrote S sub 7, and it's going to be S sub 6. Okay, it's going to equal the first term, 36 meters, right? 36 times the ratio of 1 minus r to the 6th, right? R to the n over, oh, well, wait, we know what r is, 0.9. Why don't we put r in there, shall we? Yes, we shall. 0.9 raised to 6 over 1 minus 0.9, right? And so this is going to equal, I don't know what that is, let me see. It's 1 minus 0.9 raised to the 6th, which is 0.468559, divided by 1 minus 0.9, which is just going to be 0.1, and that's going to be 4.68559. Okay, and then we multiply that by 36. And I get 168. About 168.68124, but I'll just make that 0.68, I don't know, meters. Okay, so that's, you know, just the sum of the first 6 terms of that sequence. Okay, that's D, and we'll see. If the ball continues to bounce in this manner until it comes to rest, how far will it have traveled up and down from the time it was dropped from the window? Will the series converge? Oh, yes, it will. Yes, it will. It will converge because r is less than 1. Ha! Cool. And what's it going to converge to? The limit, okay, as n approaches infinity of the partial sum is going to be, isn't it going to be just t sub 1? I just love this, that it's going to be 36 over 1 minus 0.9. Look how simple that is. It's just so beautiful. So it's going to be 36 divided by, and then 1 minus 0.9, 0.1. Bam, 360. So it's gonna converge to 360 meters. So about right there, the bounces are going to be so little, it's not traveling up or down anymore, really. It's going to get, yeah, it's a good problem. All right, we're done.